So now the Apollo spacecraft spent 2 hours in the outer electron belt? Again, it depends on the source. This data is supposed to have come from NASA, so why is there conflicting information? And as we've seen, estimates are anything but reliable. And where is Dr. Van Allen's scientific paper refuting his own work? To say it in an email doesn't qualify, and there are questions as to the source of this email. At any rate, an email refuting a previous scientific paper is not exactly considered part of the scientific realm. Given what we've established here, Dr. Van Allen's original remarks in his scientific paper in 1959 about manned missions traveling through the radiation-free zone over the poles, which seemed the most logical and safest, that is, going around the radiation belts, not through them. Barbara P. Pope writes, "The sight of Armstrong walking on the moon was so unbelievable and amazing that there were those who refused to believe the images they saw and swore that the landing was a hoax and a conspiracy." It's interesting that Pope, a retired employee of NOAA, actually said that it makes you wonder why a scientist would even mention the word conspiracy. Is she hinting at something? Quite possibly, as you'll see in her next quote. Apollo 11 turned out to be a string of lucky Apollo missions that were not hampered by space weather events, which was something of a miracle. Any number of space weather disturbances could have endangered the lives of the astronauts either directly or by damaging equipment. Now there's a quote that lacks confidence, if not downright skepticism, about the validity of the Apollo missions. On August 30th, 2012, NASA launched the Relativistic Electronic Proton Telescope, REPT. A NASA article says that before REPT was activated September 1st, 2012, solar activity on the Sun had sent energy to Earth, causing the two existing radiation belts to increase in size. According to NASA, it is this energy that caused the formation of a third radiation belt. NASA says that this newly formed belt lasted approximately 4 weeks. Here's proof that as recent as 2012, NASA had ever considered the possibility of a third radiation belt formed from solar storms. Then something happened that no one had ever seen before. The particle settled into new configuration, showing an extra third belt extending out into space. Within mere days of launch, the Van Allen probes showed scientists something that would require rewriting textbooks. This quote from the article on NASA's website throws into question decades of research regarding the Van Allen belts. And it's not a very confident statement coming from a space agency that claims it solved the problem of sending manned missions through the Van Allen belts 50 years ago. It further shows that NASA had no way of knowing if another radiation belt had formed by August 4th, 1972 SPE, 4 months before Apollo 17. It also appears that NASA hasn't learned much from Operation Argus and Operation Starfish Prime either. As we've established with Operation Starfish Prime, as of 2012, that's 4 radiation belts, not 3. Kelly Smith, the NASA engineer in the YouTube video previously mentioned, uses terms like extreme radiation and dangerous radiation to describe the Van Allen belts. Further on his video, he says, "We must solve these challenges before we send people through this region of space," when talking about the Orion spacecraft. Apparently, they solved the problems during the Apollo missions, but for some reason, these problems need to be solved again? Given all the facts, the evidence proves that none of the Apollo missions traveled through the Van Allen belts. Chapter 5. Shielding for Radiation, Thermal Control, and Micrometeoroids. Some tinfoil should do it. As Chapter 4 has shown, the Apollo spacecraft had inadequate shielding for the radiation it would have encountered in the Van Allen belts, GCRs, SPEs, and CMEs. Also, as discussed in this chapter, the August 4th, 1972 SPE had an intensity of 960 rems, that is, depending on your source. To attenuate 960 rems to 40 rems, an amount considered acceptable levels for the astronauts, the Apollo spacecraft would have needed approximately 4 inches of aluminum shielding. That's still a high level of radiation to be exposed to when encountering an SPE, given that the dosage accumulated would have depended on the duration of the astronauts had been exposed to in the intense radiation. Note: the standard allowable dosage for employees working with radioactive materials is 5 rems per year. Given the real possibility that the Apollo astronauts would have encountered an SPE, and that NASA says the CM shielding would have attenuated radiation down to approximately 40 rems, that's still a dose of radiation equivalent to 8 times the allowable yearly dosage as set by the governmental regulation agencies. However, the duration of exposure to 40 rems needs to be taken into consideration. The fact that there would have been substantial damage incurred by the astronauts remains uncontested, the main point being that no one, not even experts, can talk in definite terms regarding terrestrial and extraterrestrial radiation as its effects on people, especially those that were part of the Apollo missions beyond LEO. John H. Malden has a master's in physics and a PhD in science education and is also a former employee of NASA. His responsibilities included work on the Voyager missions. He made some interesting remarks about the required protection from radiation for manned missions. Malden writes, "By comparison, solar flares can deliver GeV protons in the same energy range as most of the cosmic particles, but at much higher intensities. Increase of energy accounts for most of the increased radiation danger because GeV protons or their products will penetrate several meters of material. As for GCRs, cosmic particles are dangerous, come from all sides, and require at least 2 meters of shielding all around the living organisms." Proponents of the Apollo missions have pointed out that Malden is talking about interstellar travel and that enormous distances between solar systems are far greater than interplanetary travel, therefore requiring more shielding than is needed for manned missions to the Moon and to Mars. Therefore, the proponents are insinuating that radiation intensities are different depending on the area of space that a mission is traveling through. That insinuation is partially true, but it does not represent the whole picture. Are SPEs any different in intensities between the Earth, Moon, and Mars? One could argue correctly that SPEs are more intense between the Earth and the Moon given their closer proximity to the Sun. In fact, when talking about SPEs, Malden points out that SPEs can give a dose of hundreds to thousands of rem over a few hours at a distance of miles from Earth. No one needs to be an expert to know what hundreds of thousands of rem over a few hours can do to human beings. As shown in Chapter 4, NASA tends to give the impression that by calling space between Earth and Moon cislunar space, the elements that could be encountered by manned missions to the Moon is somewhat less intense than deep space manned missions, which is not entirely accurate. Are GCRs any different in intensities inside and outside of our solar system? GCRs are no less dangerous in our solar system, even when we factor in the solar cycle of the Sun. In fact, when it comes to shielding spacecraft, especially unmanned missions anywhere in cislunar space and beyond, it is the mass and density of the material that is the important factor in protecting the astronauts. Ralph Renee writes, "It wouldn't matter if the shielding material was made of lead or not. Radiation shielding depends mostly on the mass and density of the material that is between the source and the victim. Lead is effective because of its high density. On an equal basis, a layer of water is even more effective, despite its lighter mass, but lead is less bulky. Of course, to launch a spacecraft shielded by the added weight of water or lead would far exceed the lift capabilities of any rocket design in existence. And as we have discussed in Chapter 2, the heavy lift capabilities of the Saturn V, the most powerful rocket ever designed and built, as is claimed by NASA, couldn't even make it to low Earth orbit because of its unstable F1 engines. Aluminum shielding thickness is most effective at stopping primary heavy nuclei, the type of cosmic radiation that causes the most damage to living tissue. Components of the annual cosmic ray dose equivalent versus shielding thickness are shown at a time of minimum solar activity. High-energy protons interact with shielding material to generate additional secondary particles. With about 7.5 centimeters of aluminum, the normal dose equivalent is reduced from 50 rem to 35 rem. Calculations for a very large solar flare series like the events of August 1972 show that the lethal unshielded dose of about 1000 rem is reduced to 40 rem with 9 centimeters of aluminum shielding. As has been made clear, the Apollo CM and particularly the LM had nowhere near the shielding necessary to attenuate radiation to 40 rems. However, the CM might have had the protection it needed had it stayed within the relative safety of low Earth orbit, well under the Van Allen belts and within some protection of the Earth's magnetic field. So, the only protection the CM and LM would have had with an SPE like the intensity of August 4, 1972 SPE is to avoid it, and given the level of technology used in the Apollo missions, that would have been impossible. NASA said that it had procedures for the astronauts to follow in the event of an emergency like encountering an SPE. For example, a radiation survey meter, RSM, is taken on each Apollo mission. The RSM is a direct reading dose rate instrument that allows the crewmen to determine radiation levels in any desired location in their compartment. The crewmen would use the RSM to find a habitable, low-dose region within the spacecraft in the event of a radiation emergency. When one checks out the actual dimensions of the crew compartments in both the CM and LM, one has to wonder where exactly a habitable low-dose region within the spacecraft in the event of a radiation emergency would be located. Aside from exposures to the Van Allen belts, GCRs, SPEs, and CMEs, the Apollo spacecraft would also have had to contend with thermal control and micrometeoroids. For thermal control, there's still a debate as to the best methods of controlling spacecraft temperatures while in low Earth orbit and beyond, although seemingly this debate was resolved during the Apollo missions, and it is common knowledge micrometeoroids can be a hazard to any space mission, whether manned or unmanned. With an adequate shielding, a high-velocity object in space can penetrate a spacecraft with catastrophic consequences, in addition to what it would do to any astronaut on an extravehicular activity EVA. We will be discussing thermal control and micrometeoroid protection in this chapter. Any one of these 6 space environmental elements, the Van Allen belts, GCRs, SPEs, CMEs, thermal control, and micrometeoroids could have ended a mission in minutes or even seconds, let alone encountering all 6 of these elements at once. Thus, to appreciate the complexity and seriousness of any of these elements in the space environment, we must first review the shielding of both the CSM and LM. As we continue on, it will become evident that neither the CSM or LM had anywhere near the protection needed for any of the elements of space environment as mentioned above. Command and Service Module dimensions and shielding. The CM consisted of 2 sections, the SM and CM. The SM was 24.93 feet in length with a diameter of 12.79 feet. It was made of 1-inch thick walls comprised of aluminum alloy honeycomb panels. It was divided into 6 compartments, 4 of which carried the propellant needed for the 20,500-pound Thrust Service Propulsion System SPS engine. The 5th compartment contained the fuel cells and the reactants needed for the electrical power, life support systems, water management, and air temperature regulation. On Apollo 11, the 6th compartment was left empty. On later missions, the 6th compartment was used to carry the Scientific Instrument Module SIM. The SM also carried most of the communications as well as the reaction control system for attitude control. The aluminum alloy honeycomb panels would have needed to protect the propellants and communications equipment for all of the 6 space environmental elements mentioned. The CM had a height of 10.56 feet with a diameter of 12.82 feet. Its structure consisted of an aft heat shield, the pressurized primary structure of the crew compartment, a central heat shield over the primary structure, and a forward heat shield which housed the docking mechanism and the parachutes needed for the eventual splashdown into the Pacific Ocean. The inner pressurized crew compartment was constructed with lightweight double-skin aluminum alloy material. The non-pressurized central heat shield structure consisted of fiberglass honeycomb bonded to a steel honeycomb material covering the primary structure. It is this outer layer of the CM that NASA claims provided protection from radiation, thermal, and micrometeoroid exposure. The combined thickness of the material used to construct the inner and outer walls was from 1.10 to 1.5 inches thick. There were 5 windows, all made with triple layers of glass, the outer one being 3/4 inches thick. The actual space available to the astronauts was approximately 210 cubic feet, which is about the size of an average car. The overall protection of the CM consisted of the forward heat shield, the material around the main part of the spacecraft, and the aft heat shield. The aft heat shield's primary purpose was to provide protection from the fiery re-entry into Earth's atmosphere. The aft shield was made of material that charred and burned away in a process called ablation. The material used in the aft heat shield was up to 2.5 inches thick. For the purpose of this chapter, our discussion will focus on the effects of radiation, heat, and micrometeoroid impacts on the CM and LM in cislunar space. The aft heat shield will be discussed in detail in part 2 of this series. Lunar module dimensions and shielding. Like the CM, the LM had two sections, the descent stage and the ascent stage. The descent stage was approximately 12 feet in diameter and 31 feet diagonally across the landing gear. It was divided into 4 quadrants which contained the 4 propellant tanks and the supercritical helium tank. It also contained the 10,000-pound thrust engine used for lunar orbit and descent to the lunar surface. The primary structure consisted of aluminum alloy, which was also covered with 16 layers of golden mylar aluminized foil. It is these layers of mylar aluminized foil around the descent stage which is supposed to have provided the necessary thermal and micrometeoroid protection. The ascent stage had a height of 12.34 feet. This contained the crew compartment, which had a horizontal shape within a diameter of 7.67 feet and the length of 3.5 feet. It also contained a 3,500-pound thrust engine needed for launch from the lunar surface. The structure consisted of aluminum alloy and had 2 triangular forward-facing windows and 1 docking window above the commander's station. The skin of the LM cabin was just 0.012 inches thick. In the end, the lander became a strange mix of strength and fragility. The skin of the descent stage was only a mylar wrapping stretched over a frame. In the ascent stage, the walls of the crew cabin were thinned down until there was nothing more than a taut aluminum balloon, in some places only 5/1000th of an inch thick. Once, a workman accidentally dropped a screwdriver inside the cabin and it went through the floor. Now in space, it seems deceptively flimsy. When the cabin was pressurized, the front hatch bulged outward. That had scared John Young, who was in the command module wearing nothing but a pair of long johns. He was up muttering, "I didn't know I was volunteering to go on this damn thing in my underwear." No wonder Jim McDivitt called this LM the tissue paper of spacecraft. But it was sturdy enough, even more than enough, for the moon. Directly over the crew's heads was the hatch that provided access when docked to the command module through a tunnel. The crewmen stood in the lunar module looking forward through a small triangular window on each side, with the commander on the left and the LM pilot on the right. The external skin of both stages was paper-thin aluminum. The lower stage was covered by multiple layers of gold mylar insulation. You could easily poke a pencil through the side of the spacecraft. Portions of the interior were covered with netting to save weight and catch anything that might fall into the nooks and crannies inside of the LM. Designed to operate only outside the Earth's atmosphere, the LM looked ungainly and had no heat shield and was incapable of safely entering the Earth's atmosphere. As you can see from the above section, the Apollo CM had nowhere near the shielding protection necessary to attenuate radiation to acceptable levels. Add to this the windows in both the CM and the LM and the overall shielding necessary to protect the astronauts from intense radiation and/or micrometeoroids didn't come close to the level for protection that would have been needed when compared to what was mentioned above by John Malden. The materials used to make the CM walls were 1.5 inches thick, which included the aluminum alloy and honeycomb panels. Aside from John Malden's recommendations, this doesn't even come close to the 4 inches of aluminum or more that would have been needed to attenuate intense radiation encountered in SPEs to acceptable levels for the astronauts' safety. As for the LM, the walls were so thin that you could easily poke any object through them, causing a rapid decompression, instantly killing the crew had they not been wearing their spacesuits. In other words, all that separated the two astronauts in the LM from that of the vacuum of space were the cabin walls equivalent to the thickness of 3 layers of kitchen foil. The LM and its flimsy design will be discussed in part 2 of this series. In the next section, we'll discuss the issue of temperature in space, including whether it's hot, cold, or neither, and why the importance of thermal control would have been another necessary part for any Apollo space mission to have succeeded. Temperature in space. We often hear about the extreme coldness of space and how anything exposed to this environment will freeze. That's not entirely accurate in our area of space. Earth's atmosphere diffuses heat more evenly because of conduction and convection, but the vacuum of space for the most part is devoid of matter, so therefore it can be better described as neither hot or cold. Being that the Earth and the Moon are approximately 93 million miles from the Sun, the effects of temperature are a constant threat for space missions in LEO and beyond. In LEO, spacecraft would spend half of their orbits exposed to the Sun with temperatures on the outside of the hull reaching as high as plus 200 degrees Celsius while reaching minus 200 degrees Celsius in LEO away from the Sun. But in cislunar space, the aircraft would be constantly exposed to the Sun, increasing temperatures on the outside of the hull. In addition, the area of space around the spacecraft would act like an insulator, adding to the problem of heat buildup within the crew compartment. The analogy of a thermal flask best illustrates the problem. The area between the inner and outer sections of the thermos flask is devoid of any of the outside atmosphere, in effect a vacuum. Therefore, heat in the inner section cannot be conducted outside, keeping hot liquids close to the same temperature for hours. This can be compared to the vacuum of space around the spacecraft. The spacecraft would lose heat through radiation, much like the thermos flask. So in effect, the vacuum around the spacecraft becomes an insulator. Here's what's going on. Most of the gas in space is too thin to warm anything up. Essentially, there is not enough gas particles to bump into and transfer the heat to an object. So if you were in space, but shielded from the Sun, you would radiate away nearly all of the heat quickly and cool to the cosmic background temperature. Step or float into the Sun, and you'll be warmed. Either way, you'll need lots of protection. If the Apollo missions had really circumnavigated the Moon, the problem would be to have to prevent the CM and the LM from getting too hot or too cold. The Apollo spacecraft would constantly have been bombarded by the Sun's rays on one side of the outer hull en route to the Moon, with the same conditions on the way back to Earth, reaching temperatures as high as plus 200 degrees Celsius or more. The opposite side of the CM and the LM would have been cold by comparison, since the vacuum of space cannot conduct heat from the side facing the Sun. In addition to this, the CM crew compartment atmosphere would have acted like a conductor, heating all areas of the CM interior. Although there would have been heat loss through radiation on both sides of the CM and LM, the constant bombardment of the Sun's rays would have been a constant source of heat, causing a buildup of temperatures to dangerous levels that would have eventually killed the astronauts. As the above quote says, step or float into the Sun and you'll be warmed. Either way, you'll need lots of protection. However, NASA says that it solved this problem through environmental and thermal control. The environmental and thermal control aspects of any spacecraft depends on whether its mission is in LEO or beyond. We'll discuss the thermal control aspects of the Apollo missions in the area of space between the Earth and the Moon, that is, cislunar space. The Apollo spacecraft environmental and thermal control, deflecting radiation and regulating the temperature from the Sun's heat as well as heat produced from the inside of the CM would not only have been imperative for the safety of the astronauts, it would have been essential for the proper functioning of the power systems of the Apollo spacecraft. The instruments and computers for both the CM and LM would have needed to be maintained at a temperature conducive to the astronaut's safety. Since conduction and convection are absent in the vacuum of space, the thermal control system had to be designed to reject the excess heat into space while maintaining appropriate temperatures inside of the Apollo spacecraft for all phases of the mission. Therefore, this along with many other considerations would have been needed to have been factored into the design of the CM and LM. A malfunction of the environmental and thermal control system alone would have ended any Apollo missions in hours, possibly minutes. Hence, considering the vast distances between the Earth and the Moon for our level of technology, there would have been no possibility of an Apollo mission making it back to the Earth safely in event of an environmental and thermal control system failure. In LEO, the astronauts may have survived a partial failure of the environmental and thermal control system in the CM, where emergency procedures could at least be implemented for a re-entry and an eventual splashdown. The atmosphere revitalization system and the thermal control system is another of many aspects of the Apollo CM and LM that would have had to work to near perfection since, as we previously established, there is little or no redundancy in the design. Atmospheric Revitalization System. The Atmospheric Revitalization System, ARS, was there to regulate the temperatures for the heat produced inside the CM. For example, heat produced from the instruments and components necessary for the proper function of the spacecraft would have had needed to be radiated and/or routed to mechanisms that would have rejected the heat to the vacuum of space. Carbon dioxide and humidity produced by the astronauts would have needed to be removed too. All of this would have had to be done on a continuous basis. The ARS involved heat exchangers, electrical heaters, and water glycol coolant loops. The heat exchangers were used to heat the crew compartment if needed, with the electrical heaters used as backup for more heat if necessary. To help regulate the temperatures for astronaut safety as well as for the proper function of the CM and LM, coolant loops would have cooled the electronics. This excess heat was then routed to radiators in the service module and emitted through radiation out into space. This, of course, is how the ARS was supposed to have worked according to the few NASA documents still available. Thermal Control System. The Thermal Control System, TCS, was used to help regulate and deflect heat, mainly from external sources such as the Sun. The design of the Apollo spacecraft, TCS, included mylar foil coating applied to most of the surfaces of the CM and LM. The mylar foil coatings help to deflect heat from the Sun's solar rays. However, degradation of the thermal coatings would have needed to be factored in on any of the Apollo missions, since long-term working solutions for these coatings had yet to be found. The boost protective cover over the main CM structure helped to protect the thermal coating during launch, which was then jettisoned before orbital insertion. But given the unpredictability and variations of the harsh environment of space, calculations needed to be precise, since any estimates would have been inadequate. Any encounter with one of these 6 space environmental elements would have required immediate action on the part of astronauts, although GCRs would have constituted a constant threat. This would have required the response time of an autonomous computer equipped with sensors capable of determining the degradation or damage done to the protective coating and/or shielding, and then communicating that information to the astronauts. Of course, as has been established in Chapter 3, the AGC do not have this capability. As one side of the CM and LM would have been facing the Sun en route to the Moon, a method had to be devised to even out the heat around the CM and LM's hull. To prevent one side of the spacecraft roasting and the opposite side freezing in the constant sunlight of cislunar space, it was oriented with its principal axis perpendicular to the ecliptic, then set on a 20-minute cycle for passive thermal control, PTC, in a regime more popularly known as the barbecue mode. This had to be established before the astronauts could retire for the night. After launch into LEO of the Saturn V, it would have been long before the CM had fired its engines for TLI into cislunar space, so if a passive thermal control, PTC, was necessary to help even out the temperatures of the CM, one wonders why this needed to be established before the astronauts could retire for the night, and not before, since it would have taken long for the CM to heat up owing to the constant rays of the Sun shortly after leaving LEO. But PTC was hardly a solution to the problem of protecting the CM from the constant heat of the Sun, and given the degradation process of the reflective mylar covering of the outer hull, this further exposed the CM to extreme heat. The slow roll of the CM and docked LM along its longitudinal axis for PTC also has its own problems. PTC supposedly worked well during the Apollo 8 mission, but according to NASA, PTC caused other problems that affected the longitudinal axis of the spacecraft during later Apollo missions, since these missions involved the LM unlike Apollo 8. This added further to problems in navigation, which could have required even more course correction. Given the tasks of maintaining precise navigation, nothing short of an autonomous computer equipped with sensors interfaced with the navigation and flight control systems of the CSM would have sufficed. As is being established in Chapter 3, crew interface was necessary for making course corrections, which is nowhere near as autonomous as the AGC should have been, aside from the fact that this computer had little or no memory for any of the tasks it was expected to do.